Think for a moment about, well, all the technology that powers our lives.
Yeah.
From the crisp images on our screens to the GPS guiding our journeys. What if I told you there's a fundamental mathematical concept, often unseen, that's woven into the very fabric of this digital world? Today, we're diving deep into polynomials, these ubiquitous yet surprisingly invisible players in the age of algorithms and AI.
That's absolutely right. Polynomials are, well, they're much more than just those algebraic expressions you might remember from school. They're really the underlying language for describing data trends, shaping the curves in computer graphics, modeling complex phenomena, all sorts of things.
Like what specifically?
Well, they're essential for computer animation, for instance.
Yeah.
And those incredibly accurate GPS systems we all rely on, even for simulating how diseases spread, believe it or not.
Ah, okay, so they're really everywhere.
Pretty much. Image processing, the CAD systems engineers use for, designing everything from cars to skyscrapers.
Weather prediction.
Yep. Weather prediction, compressing our favorite music files, underpinning engineering design, informing economic models, and crucially, driving the engine of modern AI through machine learning.
Okay, so that's a pretty broad category, polynomials in general.
Hmm.
But today we're focusing on a particularly elegant and influential type, isn't that right?
Exactly. We're zeroing in on Bernstein polynomials, a brilliant idea introduced by Sergei Bernstein way back in 1912.
1912.
Yeah, and while it might sound like some niche mathematical concept, its impact has resonated, well, really deeply across a surprising number of fields.
Okay, 1912, that's quite a history. So in simple terms, what exactly do these Bernstein polynomials do? What's their sort of core purpose?
Imagine you have a curve, right? Something you want to represent on a computer screen. Bernstein polynomials provide a way to approximate that curve using a series of control points.
Control points.
And think of it like sketching a shape by connecting dots, maybe. But instead of straight lines, you get these smooth, mathematically defined curves.
Okay.
The formula that achieves this, well, it looks like this, is basically the sum of several terms. Each term involves a Bernstein coefficient, let's call it Bisnaw true, and a basis polynomial, a dual.
Right.
And that basis polynomial itself is calculated using a combination of binomial coefficients, that's the choose part you might remember, and powers of x and 1x.
Okay, so they're a mathematical way to describe and, I guess, manipulate curves. But what made these particular polynomials so significant? Why are they still so relevant over a century later?
Well, their enduring significance really comes from this beautiful blend of simplicity and power. Initially, they played a crucial role in something called the Weierstrass approximation theorem,
Okay.
which essentially proved that any smooth curve you can draw can be approximated as closely as you like using polynomials. A fundamental result, really.
So a big theoretical breakthrough.
Yes. And from there, Bernstein polynomials evolved into a cornerstone of approximation theory, numerical analysis, which is all about finding numerical solutions to problems, and especially computer-aided geometric design, or CAGD.
CAGD.
Really.
Right. So this isn't just abstract math theory then. There are tangible, real-world benefits.
Oh, absolutely. They have some key properties that make them incredibly useful. For instance, they're always non-negative, and they always add up to 1. You can think of it like distributing a total amount, each part is positive, and together they account for the whole thing.
Like probabilities.
Sort of, yeah. It's called a partition of unity. And they also have what we call shape-preserving characteristics.
Shape preserving. How does that work?
Well, if you move those control points I mentioned earlier, the curve follows those movements in a really predictable and, frankly, intuitive way.
Ah, I see.
Which makes them ideal for mathematical modeling, fitting curves to real-world data, and solving optimization problems.
Shape preserving, that really clicks, especially when you think about visual applications.
Exactly. And this is where their close relationship with Bézier curves and surfaces becomes so important.
Right, I've heard of Bézier curves.
Well, Bernstein polynomials act as the fundamental building blocks, the basis functions for these geometric shapes. Bézier curves and surfaces are basically the workhorses of computer graphics, CAD software, virtual reality.
So, like designing things on computers?
Yes. They're the mathematical language used to create those visually appealing and precisely defined forms we see in everything from digital manufacturing, think designing parts for cars, airplanes, to 3D printing intricate objects.
It's really remarkable how an idea from, while over a century ago, still underpins so much of our cutting-edge tech.
It truly is.
So for this deep dive, what specific questions are we hoping to answer about these often unseen mathematical tools?
We decided to take a step back, look at the broader landscape. We've conducted what's called a bibliometric data analysis using the Scopus database. We looked at publications all the way back to 1949. Yeah. Our mission, really, is to understand how research in this area has grown and changed over time. We want to identify the key researchers, institutions, funding bodies who's been most active.
Oh, okay.
And pinpoint the most influential publications. And perhaps most intriguingly, uncover areas where Bernstein polynomials might be, well, surprisingly underutilized.
Oh, finding the gaps, too.
Exactly. And as far as we can tell, this is the first time a comprehensive bibliometric analysis specifically focused on polynomials has been done using the Scopus database.
That's a pretty ambitious undertaking. So walk us through the process. How did you actually sift through all that scholarly information?
Well, we started with Scopus, which is just this massive collection of scientific publications. We searched for documents that included the phrase Bernstein polynomial anywhere in the record title, abstract keywords, even full text sometimes.
It's like a broad search.
A broad search. But to keep our focus sharp, we excluded things like preprints, patents, secondary reviews. We also used a wider net of related keywords.
Why do that?
To try and capture research in more applied fields that might use Bernstein polynomials but not explicitly mention the term in the title or abstract. We do have to acknowledge, though, this might miss some really early work that used different terminology.
Right. Language changes over time, so a really thorough sweep. And what did you do once you had this, mountain of data?
We followed a pretty standard set of steps for bibliometric analysis. First, define the questions, then collect the data. The crucial part was the analysis looking for patterns, relationships within the data.
Okay.
We used a software tool called VIOS Viewer to create visual maps of these relationships. It really helps you see connections between authors, keywords, publications.
Like a network graph.
Exactly. And we also used AI chatbots, ChatGPT, Llama, Mixed-Role, Perplexity to help analyze the data and even brainstorm potential interpretations.
Interesting use of AI there.
Yeah, it was helpful. We extracted basic stats directly from Scopus and used VIOS Viewer for something called co-citation analysis. It shows us which papers are frequently cited together. That often points towards really influential works in the field.
Okay, got it. So what kind of overall picture emerged? What were some of the headline numbers that jumped out at you?
Well, as of January 23rd, 2025, the exact phrase Bernstein polynomial appeared in the title, abstract, or keywords of about 2,371 documents.
Okay.
However, when we broadened our search to look for mentions anywhere, full text, references, etc., we found a much larger number. 0 documents since 1949.
Whoa, that's a huge difference. Nearly 4 times as many.
It is, and it strongly suggests that while Bernstein polynomials might not be the central topic of many papers, they're a tool or concept that's frequently used or cited in a much wider range of research.
So they're kind of a foundational tool people build upon.
Exactly. And for our deeper dive into applications and trends, we really focused on this larger set of 910 documents.
Makes sense. So what kind of publications make up this body of research? Is it mostly academic journal articles?
Yes, overwhelmingly so. Research articles account for about 84.9% of the total. Conference papers make up around 11%. And the rest is, book chapters, review articles, entire books, that sort of thing.
And any red flags? Like retracted papers?
Interestingly, we only found 2 instances of retracted papers in that whole data set, which, generally speaking, suggests a healthy level of rigor in the research around this topic.
That's good to know. Now, thinking about where this research is coming from, which academic disciplines are most actively engaged with Bernstein polynomials?
Our analysis, which we visualized in Figure 1, clearly shows mathematics at the top. That's not too surprising, right?
No, that makes sense.
Following closely are computer science, engineering, and physics and astronomy. These 4 areas really constitute the vast majority of the research output.
And were there any fields where you expected maybe more activity or perhaps some surprising areas with relatively little mention?
Yeah, there were quite a few fields with less than 3% of mentions each. Areas like materials science, chemistry, economics, even medicine, arts, and humanities.
Really? Medicine?
Yeah. It highlights the potential,
Yeah.
Maybe Bernstein polynomials could be applied much more broadly. You can imagine using their shape-preserving properties in medical imaging, maybe, or their approximation capabilities in economic modeling. But the research activity just doesn't seem to be there in a big way yet.
Fascinating. Potential avenues for cross-disciplinary work. Now, zooming in on how the research has evolved, what do the publication trends tell us? Is the field growing?
Definitely growing. Figure 2 shows a really noticeable increase in both the number of publications each year and the variety of keywords being used. This uptick really started around the mid-2000s.
Any idea why then?
It suggests growing interest and broadening applications. It probably coincides with advancements in computing power, making more computationally intensive applications, well, feasible.
Right, more power lets you do more complex stuff. And have the key topics within the research also shifted over time? Looking at the keywords, for example.
Absolutely. When we examined the 20 most frequently used keywords, we saw a clear evolution. Older publications, say pre-2005, tended to focus more on fundamental mathematical concepts, algorithms, approximation theory itself, CAD.
The basics.
Right. But more recent publications show a definite rise in keywords like motion planning, trajectories, think, robot navigation, machine learning, neural networks.
The newer, buzzier fields.
Exactly. It strongly indicates a shift towards more applied, more computational uses of Bernstein polynomials.
So a definite move from the theoretical foundations towards practical applications in cutting-edge fields. That makes perfect sense with technology advancing.
It does.
Now, where's all this research getting published? Are there specific journals that are sort of the main hubs?
Yes, the top 100 sources, mostly well-respected journals in math, computer science, applied sciences, account for a big chunk, about 43.6% of all the documents.
Okay.
Table 1 lists some of the leaders. Prominent titles like the Journal of Approximation Theory, Applied Mathematics and Computation, and Computer-Aided Geometric Design are right up there.
Those titles fit perfectly with the subject areas we've been talking about. But you also noticed some interesting shifts within these top journals, didn't you?
That's right. Figure 3 shows the dynamics over time for the top 4 journals. We saw that mentions in applied mathematics and computation seemed to decrease after around 2015, while mathematical methods in the applied sciences showed a corresponding increase around the same time.
Any theories why?
It could be a number of things. Changes in editorial focus, maybe. Shifts in impact factors influencing where people submit, or just, evolving preferences within the research community. Hard to say for sure from this data alone.
Interesting. It's like tracking the currents of research interest flowing through different publication channels. Now let's turn to the researchers themselves. Which countries are contributing the most?
Table 2 gives a clear picture. China emerges as the most prolific, by quite a margin actually, followed by the USA and India. Turkey and Iran also feature strongly in the top 5.
So a very global interest. Were there any surprises in that geographical distribution?
Perhaps the most surprising finding was Russia's relatively low ranking. They came in 19th.
19th. But Sergei Bernstein was Russian.
Exactly. That's what struck us. We suspect this might be due to a preference among many Russian researchers for publishing in Russian language journals or other sources that aren't as comprehensively indexed in international databases like Scopus.
The database limitations again.
Potentially. To check this, we actually looked at the Russian e-library database and found a significant number of relevant publications there. So it supports the idea that there's strong Russian research. It's just perhaps less visible internationally through Scopus.
That's a really important point about potential biases in these big databases.
Yeah.
What about the institutions, the universities where this work is happening? Any standouts?
Figure 4 highlights the top universities by publication output. Interestingly, South Korean institutions lead the list.
Really? South Korea?
Yep. Followed by universities in Romania, India, China, Saudi Arabia, and Turkey. It really underscores the global nature of the research effort and maybe points to specific academic centers where this area is particularly strong.
It really seems like a truly international endeavor, contributions from all over. And what about the individual researchers? Who are the most prolific academics?
Figure 5A shows the top 10 most active academics based on publication count. And figures 5B through 5E give this fascinating look at the co-authorship network.
How does that work?
Well, these are overlay visualizations. They use color to indicate the publication year, so you can see how collaborations formed and evolved over time. Blue nodes are older collaborations, red are newer. And the size and color intensity of the nodes also reflect things like the number of publications by an author and the strength of their connections, how many co-authors they have, how often they publish together. You can really see these clusters of researchers working together.
Visualizing those networks must give a great perspective on how ideas are shared and built upon. Very neat. Now, research often relies on funding. Which agencies are backing this work?
Figure 6 and Table 2 detail the top funding agencies. The National Natural Science Foundation of China and the Ministry of Science and Technology of the People's Republic of China are clearly the leading supporters.
That's significant Chinese investment.
Very significant. It underscores China's strategic investment in mathematical and computational research. We also see the National Science Foundation from the U.S. and other international funding bodies represented, highlighting the global importance attached to this work.
It's always interesting to follow the money, so to speak. You even took a closer look at the researchers supported by the NSF in the U.S., right? What did you find?
Yes, we used those AI chatbots again to analyze the author names from publications supported by the NSF. Table 3 shows the results. While a good portion are affiliated with U.S. universities, a significant number have names suggesting Chinese origins and other international backgrounds, too.
So even within U.S.-funded research, it's very international.
Absolutely. It really emphasizes the increasingly global, collaborative nature of science, talent drawn from all over the world contributing to advancements within the U.S. system.
Highlights the interconnectedness, doesn't it? Now, shifting focus to the impact of the research. Which papers have been the most influential, the most cited?
Table 4 lists the top 10 most cited papers in our dataset. And what's really noteworthy is that 40%, 4 out of the top 10, were published in computer-aided geometric design.
CAGD again. Really central.
Absolutely central. Key titles include seminal works like Cederberg and Perry's paper on freeform deformation, Farron's contribution on triangular Bernstein-Bézier patches, and Faruqi's comprehensive centennial retrospective on the Bernstein polynomial basis itself.
So foundational texts.
Definitely. These papers have clearly laid the groundwork for so much subsequent research and application in the field.
Sounds like essential reading for anyone in CAGD.
Yeah.
You also mentioned using network visualizations for keywords. What insights did those maps provide?
Right. Figure 7 shows different keyword visualizations from Biosphere. The basic network map shows clusters of related topics. The density map highlights the most frequent keywords.
Okay.
And the overlay visualization, again using color for publication year, shows that shift over time we talked about. You see the clear trend from older, more theoretical keywords in blue, like approximation theory, to newer keywords in red, reflecting more applied areas like optimization, trajectories, machine learning.
It's like a visual timeline of the field's vocabulary changing. And what about the specific connections for Bernstein polynomial itself?
Figure 8 illustrates that. Both the singular and plural forms have strong links to keywords like trajectories, prediction, optimization, algorithms, approximation theory, and numerical methods.
All the things we've been discussing.
Exactly. It reinforces their role as a central tool in a wide array of computational and applied domains. We also look briefly at related terms like Bernstein basis and Q-Bernstein polynomial. In Figure 9, they have their own distinct but related keyword networks.
So we've seen where Bernstein polynomials are heavily used. But your analysis also explored the flip side, areas where their use seems, well, surprisingly limited. How did you identify those less explored territories?
Using Vioxx Viewer again, we can look for keywords that have relatively weak connections to Bernstein polynomial in the literature data. For example, Figure 10 shows that terms like biology and mathematical biology don't exhibit strong direct links in the Scopus data we analyzed.
Interesting.
Yeah, and a specific search within Scopus for papers mentioning both Bernstein polynomial and mathematical biology in the title, abstract or keywords, yielded very few results.
That's a definite gap. While maybe not immediately obvious, it makes you wonder, right? What about potential applications?
Exactly.
Were there other fields that stood out as having surprisingly rare co-occurrence?
Yes. Table 5 lists several others. Keywords like robotics, aerospace engineering, composite material, fuzzy logic, energy engineering. They rarely appear alongside Bernstein polynomial in the core parts of papers title abstract keywords.
Robotics. Aerospace. That seems surprising given the links to trajectories and design.
It does seem a bit surprising, yes.
Really?
And notably, there was a complete absence of co-occurrence with major scientific prize names, Fields Medal, Nobel Prize, at least in those core fields. Now, broader searches across all fields sometimes yielded slightly higher numbers, but the initial findings suggest these areas might represent real underexplored opportunities.
And that's where the AI chatbots came in again, to speculate on potential connections.
Precisely. We prompted several different AI chatbots. Okay, here are some fields where Bernstein polynomials seem underused. Can you suggest potential applications? Table sets provides links to their responses.
And were the suggestions interesting?
Oh yeah, some really creative ideas, potentially fruitful starting points for future interdisciplinary research. It's like getting a fresh perspective from a computational brainstorming partner.
It's fascinating how AI can help bridge those gaps, or at least suggest bridges. You also looked at co-occurrence with the mathematical subject classification codes, the MSC codes. What did that show?
Table 7 gives a detailed view of that. It shows how often Bernstein polynomial co-occurs with keywords related to different sub-areas within math itself. The color coding helps identify areas with low co-occurrence, shown in red, specifically in the article title, Abstract Keyword Search.
So potentially underexplored areas within math itself.
Exactly. Things like various subfields within algebra, geometry, areas where you might expect more connection, perhaps. It suggests potential niches even within core mathematics, as well as in applied areas covered by the MSc.
Interesting. Any other takeaways from the MSc analysis?
Well, we also found a strong positive correlation, 0.848, between the number of documents found searching all fields versus just article title abstract keywords. This suggests a pretty consistent pattern in how the term is used across the literature, whether it's central or peripheral to the paper's main topic.
This has been a truly comprehensive deep dive. Looking at Bernstein polynomials through this bibliometric lens is powerful. As we wrap up, what are the key sort of overarching insights that stand out for you?
I think the analysis really illuminates this remarkable journey, doesn't it? From their initial, quite theoretical conception over a century ago to their increasingly widespread application across so many scientific and engineering fields today.
Yeah, the scope is incredible.
And we've identified the key players, the countries, institutions, researchers shaping the field, and observed that clear, accelerating trend towards practical applications, especially in computer science and engineering.
And the real value here isn't just looking back, right? It's about pointing towards the future.
Precisely. By systematically identifying both the well-trodden paths and those surprisingly underexplored areas, we hope this can spark new investigations, maybe foster some new interdisciplinary collaborations.
And the AI suggestions are a good starting point there.
They really are. Those suggestions for the less connected fields offer this tantalizing glimpse into potential new frontiers for applying these polynomials.
So here's a final thought for you, our listener, to ponder. Given this foundational nature, these continuously expanding applications, what unexpected fields might Bernstein polynomials revolutionize in the coming decades? Where might they pop up next?
And maybe even what novel mathematical tools or insights might emerge from continuing to explore what seems like a mature area of math. There might still be surprises hidden there.
Yeah. Think about these silent architects shaping so much of our digital world, and consider the vast potential that might still lie within their, well, elegant and versatile mathematical structure. What undiscovered connections are waiting to be made?